Hi, I'm Ben-Yaakov. This presentation is entitled Analog Average Simulation of Digital Controller. The video is based on a paper, Generic Average Modeling and Simulation of Discrete Controllers, that was presented at the Applied Power Electronics Conference, APEC, at 2001. Now, why would we like to simulate digital system by average simulation? Well, there are a number of reasons for that. It seems that the human brain is more comfortable with analog information rather than with discrete representation of a system. Bode and Nyquist plots are really very intuitive, very easy to comprehend. We have spice-based simulators which are readily available and very user-friendly. And using the spice simulation, we can very easily do trial and error runs to optimize and tune a system. However, we should not forget that average simulation of the digital system is just an approximation. It is blind to some of the sampling issues, and also if you like to simulate the whole system, you need average models of, say, the power stage, not just the controller. The focus of this presentation is the controller. So let's have a look at a typical PID equation. We see here a constant. This is a proportional constant. This is a constant for the derivative. This is an S for the Laplace transformation variable. And this is the integral constant, 1 over S. Okay, so this is a PID in general. Now, in the discrete representation of this S domain into the Z domain, what we have here is very similar. We have a proportional constant, we have a derivative constant. However, S is now replaced by this term. What it is basically 1 minus Z minus 1, Z minus 1 being a delayed sample. That is one step delay, and this is the sampling time. And here we have the integral constant and 1 minus Z minus 1. So this is the Z domain representation of the PID controller. So we can now take this representation and turn it into a difference equation. Before that, let's just open it here and see what we get. So I'm sort of multiplying it here and combining the terms, and what we have is the following. What Z is the output, okay? So the output, now it's multiplied by this term, 1 minus Z minus 1. This is the input, and now the input is multiplied, first of all, by this constant. This is just accumulation of these constants, this constant, plus a term times Z minus 1, this is one delay, and then another constant, this is the derivative, times 2 delays. Okay? Now we can go and translate this Z domain into the difference equation, when n minus 1 denotes a sample, the previous sample. Okay? So now we have the present value of y is equal to the previous value, previously sampled value, times the constant, times the input, present input, and then another constant times the previous input, and then another constant times the sample 2 steps before. The key to simulating then the PID controller is actually the delay. We need an analog circuit that would mimic a delay in the Z domain. However, here it will be an average representation. And the easiest way, of course, is to use a delay line. Okay, so what we have here, this is an input. This is just a buffer, not to load the input. and get a low impedance input into the delay line. The delay line has a characteristic impedance of 50 ohms, so it is loaded by 50 ohm. There's another buffer so as not to load this point by whatever it's going to be here. So what we have here is basically an analog representation of a signal that goes in, and what we see at the output is a delay of this signal. That is, this signal is delayed by, well, n minus 1 in the discrete domain, and here it will be by the delay time of this line, which in this particular case is just defined as 100 microseconds because it's a parameter. So this is the key element that we need in order to convert the digital PID into an analog equivalent. So let's see how we do it. Again, we have this equation here, and what we see here is that the output is equal to the previous value of the output plus the terms times the input, etc. Let's have a look here and see one-to-one what is happening in this circuit diagram. This is the input, and this is the output. This is X, and this is Y. Okay? Now, let's have a look at this term here. We see a constant times the present input. This is the input, just a buffer, and this is now the constant. And here I have this term here. This is this term here. Then we have another constant times the value of X n minus 1. This is the previous sample. Okay? So we need a delay here. This is the present one, and this is a delayed one. And the delayed one now is multiplied by this constant. This is this thing here, and it's found here. Now, another term here is Kd over Ts times two delays. We have one delay, another delay, and then it is multiplied by this constant. Here it is. And then we add this thing to this part, but this has a minus sign. Okay, it's a minus sign here. So we add here and a minus sign here. So this is combining this and this. And as we combine these, we have to add it to this term. Okay, so this is this term. We add these two to this term, and it is done by this summing point. And now we are left with the last portion here. What it says here that we have to add the value of y delayed to the whole thing. Okay. Now this is y. This is a buffer, so this is y, and this is the value, the output. This is the delayed output. So we add the delayed output, this is the delayed output, to whatever we have found here. This is the whole thing here. So this is summing up this portion here with this portion here, and we got the output. Okay, so this is a way to get an average circuit that represents the PID, the digital PID, with the delays which are built by the delay lines. Another element that is used in digital control is the sample and hold. A sample and hold is basically a circuit. This is a switching circuit, a generic switching circuit. We have a switch here, and the input is sampled, and it is stored here, and we get it output here. The rate here is the sampling rate, and so if the input, let's say this is the green, the blue one is the input, and the stepwise is the output here. That is, we sample here it stays constant, then we sample here, it stays constant, etc., etc. Okay? Now, what we would like to do is also build an average model of this thing so we can incorporate it with the PID or with any other controller. Now, as it turns out, the S-domain representation of the sample and hold is this thing here. What it says here that we have a constant minus e to the power of minus st. This is a delay of ts. And then it is divided by st, which is basically an integrator. So we have 1 minus a delay and then an integrator. And here it is. We have the input as it is. This is the 1 here. And we subtract from this input the delayed value of the input. This is the input and this is the delayed value, and we subtract it. And then the whole thing is multiplied by the integrator, 1 over st. This is the integrator, this is the constant of the integrator, 1 over t sub s. Okay? So this is a analog representation of the zero order hold. And we see here some examples. We see, as we've seen before, the blue one is the original, the input. The step 1 is the time domain sample and hold, zero order hold, and the brown one is the average. So what we see is that we get from the steps, we get just an average value. This is the output here, okay? These are the average value. Now, if the sampling time is sort of coarse and it's long as compared to the signal itself, we'll see steps like this, and then the average will be again something of this nature. This point is the average between this, and this is the average between this and this. Okay, so this is the time domain sample and hold. This is the average circuit, average simulation circuit. Now let's have a look at the actual simulation of a in this case, boost converter. This is a simulation in the time domain, a switching circuit. I'm not showing all the details because this is a little bit outside of this subject matter of this presentation. What it is, we have here the input inductor. This is a generic switch, a diode. This is the output section. Here we have a means of loading, a step load to the output to see the dynamics. This is a reference, comparing the output to the reference, and then it goes into, this is a sample and hold, zero order hold here, and this is a digital PID, not shown the detail, just a block of it, and then it goes into a block of a PWM modulator to turn on and off this thing. So this is a closed loop system of a boost converter. Now this will be an average model. Again, I'm not showing all the details. You can look at a video on an average simulation that I've also posted. This is an average model of the boost. Again, I'm not showing the details. Again, this will be the load step arrangement, the reference. Now, this is an average zero order hold, as we have seen it before. This is an average PID controller, and this is an average PWM modulator. Now, this is the duty cycle, but this is a average model, so therefore this is not, we don't see pulses here, but rather a continuous waveform voltage, and it is coded, that is the duty cycle is coded into volts. Say 1 volt is duty cycle of 1, 0.5 volt is duty cycle of 0.5. Okay, so this is a average model of a closed loop boost converter. What is shown also here is a way to get the loop gain by simulation. What we do, we add here a junction, we inject an AC, this will be an AC run simulation, and then it can be shown, again I'm not elaborating on it, that the ratio between the voltage here and the voltage here is in fact the loop gain. Okay, and here indeed we see the loop gain as measured by this method. The brown one is the gain and the green is the phase. This is the 0 dB here, there's crossover. This is the phase, so this is the phase margin of the system. Now here we see a comparison in the time domain between the average and the switched circuit. Okay, so this is the same circuit, only one is a digital simulation, the other one is the average model of the system. And as you can see, it's a pretty good match, except for the very harsh transient here. The very beginning, there's some mismatch, but overall, it's a very good match. So the average model is really following the actual digital, real, physical system. Let me now do some simulation, and I'll just demonstrate simple simulation of the zero order hold circuit. This is the delay line, and this is the 1, and here minus the delay times the integrator. This is the output. Okay, so this is a zero order hold. Now, the excitation here, actually there are two sources, one for a transient or time domain analysis, V sine. It has an offset of 1 volt, amplitude of 10 millivolt, this is the sort of superimposed on the 1 volt, and a frequency of 20 kilohertz. TS, this is the delay, set here to 10 microseconds. The other source is for the AC analysis. This is just one AC, and it's going to be swept over the frequency. So let's start with the transient analysis. Let me just have a look at the setting, because there's an important point here. Well, first of all, let's see, we're going to run it for 300 microseconds. I've also set a maximum step size of 10 nanoseconds, but it is very important to check this box. If you are not checking it, it means that it's going to calculate the initial condition. You don't want it to do it. You want to leave the situation as it is at 0 time. Let me explain why this is it. If the system will actually calculate the steady state situation at 0 time, then if there is a 1 volt here, there's a 1 volt here, then it'll calculate a 1 volt here, because this is the state, the stable situation at 0 time, static situation. However, in the real run, this value here is 0, because at 0 time you have only this part coming in, and since no time has passed, this is still 0. Only after this delay you are supposed to have a value here. Okay? So if, however, you'll get 1 volt, say if this is 1 volt here, you'll get 1 volt here, then the difference will be 0, and you'll get 0 output, which is incorrect. Okay? So it is very important to check this thing, to skip initial transient bias calculation. Okay, so let's have a run, and here it is. The green one is the input, and the red one is the output. Here we see how it stabilized during the delay time, and then we get this difference. Again, this is a smooth line, a smooth curve. It's supposed to be stepped in the real world, but this is an average representation, so we see it a smooth curve, and of course this difference is the delay due to the sample and hold, zero order hold mechanism. Okay, let me now run an AC analysis. Have a look at the setting. It's at 10 hertz to 10 megahertz, 100 points per decade. Just a simple sweep. So here it is. We see the AC value of 1 volt up to about 10 kilohertz, and then it starts to roll off. There is a 3 dB point here, and then we have a notch at 100 kilohertz because the delay is 10 microseconds. Okay, this is very typical of a zero order hold, so it looks very nice, and in fact you can understand what is really going on as far as the bandwidth is concerned. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found this presentation interesting and that it will be useful to you in the future. Thank you.